Welcome back to another episode of Practical Electronics and Circuits 101. In this series, I explain the fundamentals of electrical engineering with a focus on using this knowledge for actual projects. In today's episode, I'll be giving an introduction to oscilloscopes, which are commonly referred to as O-scopes or simply scopes for short. Scopes are a very powerful tool that are used to measure signals and to gain a visual representation of them, and are very complex devices that can do a lot of advanced functions. But these more complex functions actually aren't necessary in a lot of cases. Unless you're an engineer working on some really advanced projects, scopes are actually pretty straightforward to use. So that's what I'll be focusing on in this video. I'll be explaining the fundamentals so that by the end of the video, you should have a solid understanding of how to use the basic functions of a scope for your own projects and for the sorts of projects I have planned for the channel. Other than a scope, the only other measurement tool you really need for electronics projects is a multimeter, which I've covered in a previous video. The link to the full playlist is in the video description, so if you haven't seen the previous videos yet, then I highly recommend watching them as well. Alright, so let's begin by going over what oscilloscopes are, what they do, and give a little history and background on them, and then I'll give a demo showing how to use the basic functions of a scope, and I'll also give some recommendations on which one to buy if you're in the market for one. Now, like I mentioned a minute ago, scopes are used to measure signals and to gain a visual representation of them. But to be more specific, they measure the voltage of a signal in the time domain on a graph. So in other words, the y-axis of the graph is the voltage, while the x-axis is the time in seconds. This information is extremely useful in a wide range of applications that involve signals. To give a few examples, every digital system contains at least one clock signal. The clock is a square wave that operates at a certain frequency, and there are many cases where you'll want to verify the frequency of a clock, in which case you'll use a scope to do this measurement. Another example could be a PWM signal, which is also a square wave that can vary in both frequency and duty cycle. And many devices such as servo motors require a specific PWM frequency in order to operate. So it's common to verify your device is outputting the correct frequency with the scope before connecting it to the servo. By the way, I'll be covering motors and servos in my next video, so stay tuned for that. But anyway, scopes aren't just useful for digital systems, they're also used to measure analog signals. For example, on the left side here we have a simple sine wave, and on the right side we have a more complex audio signal captured from music. These are just a few examples, but like I said, scopes are used to measure all types of other signals as well, and being able to see a graphical representation of a signal provides valuable information and insight. Later in the video, when I demonstrate how to use the basic functions of a scope, I'll also explain how to read the graph in order to calculate the frequency and amplitude of a signal. But right now, let's go over a little history of scopes and their origin. The first oscilloscope was invented by French physicist André Blondel back in 1893. But unlike later oscilloscopes, this one was a mechanical device that recorded information using an ink pendulum that would write onto a moving paper, similar to how a seismograph works, which is used to record earthquakes. However, Blondel's scope was extremely rudimentary, wasn't very accurate, and had very limited bandwidth. Bandwidth is one of the most important specs to consider when comparing scopes. A scope with a higher bandwidth will be able to measure higher frequencies, and generally speaking, the more expensive a scope is, the higher its bandwidth capabilities will be. But anyway, only 4 years after Blondel created the first oscilloscope, German scientist and Nobel Prize winner Carl Ferdinand Braun demonstrated the first cathode ray oscilloscope, which was able to electronically display a graph of the signal. This is the same technology used in CRT televisions, and CRT oscilloscopes would become the standard for many decades, until they were eventually replaced by LCD screens and digital scopes. After World War II and the invention of the computer, the need for more advanced oscilloscopes became extremely important, and they became an essential tool for any engineer who worked with electronics. For the next few decades, there were major advancements made with new scopes offering higher bandwidth, lower noise, additional features, more channels, and shrinking them down to a more portable size. They also became easier to use and more intuitive with how their knobs were designed, allowing users to easily scroll and zoom in on various waveforms. Keep in mind that during this era, scopes were completely analog devices, which means they didn't contain any computers. These were incredibly complicated devices to design and build, and had extremely tight tolerances since they're lab-grade equipment, which means they came with a hefty price tag as well. Even back in the 70s, it wasn't uncommon for a good scope to cost tens of thousands of dollars. So just do the math on what they would cost today after adjusting for inflation. Now, by the 1980s, digital technology advanced to the point where digital oscilloscopes became a possibility. But the first few generations of digital scopes were inferior to older analog ones. At the heart of every digital scope is an ADC, or analog to digital converter. The bandwidth of a digital scope is directly dependent on its ADC's sampling rate, which determines how quickly the ADC is able to make a measurement. The higher the sampling rate, the higher the scope's bandwidth, and this concept follows the formula known as the Nyquist theorem. The Nyquist theorem states that an analog signal can be digitized without aliasing error if and only if the sampling rate is greater than or equal to twice the highest frequency component in a given signal. So to give an example, in order for a digital scope to measure, let's say, a 1 MHz signal, its sampling rate needs to be at least 2 megasamples per second, or in other words, 2 million samples per second. But as we all know, computer technology rapidly advanced during this time. So by the 1990s, digital scopes started becoming good enough to replace analog scopes. But of course, these weren't cheap either, and even today, a good lab-grade scope can easily cost several $1,000s. But not everyone needs such advanced scopes, and there are also much more affordable options these days for hobbyists and for applications that don't require extremely high bandwidth. So now let's go over some of the options that are available today if you're in the market for one. I spent some time researching different scopes and reading reviews before coming up with this list, which contains affordable scopes from about $40 up to about $350 on the high end. If you're serious about learning electronics and working on projects and have the money to spare, then I suggest buying one of the more expensive scopes so that you won't need to worry about running into limitations, especially when it comes to bandwidth. But even the cheap handheld scopes I'll be showing here are extremely useful for many different projects, and are nice to have even for engineers, because of their small size and portability. Also, I'll include Amazon affiliate links in the video description for the scopes I'll be showing, so if you want to help the channel out, then be sure to use the included links. Alright, so let's first start with the low-end portable handheld scopes. The first one on the list is the Z-Way 154 Pro, which advertises an 18 MHz bandwidth, which is pretty impressive given the low price tag of around $40. Its small size and battery-powered operation means it's completely portable, unlike the traditional benchtop scopes which require a power outlet. A few accessories are included such as an alligator clip probe, a traditional style probe, and a USB cable to charge the battery. It also comes with a built-in multimeter and signal generator, which is something you actually won't find in the expensive lab-grade scopes, but rather, signal generators are typically purchased as their own standalone unit. Signal generators are used to create various waveforms including sine waves, square waves, sawtooth waves, and more. And these are useful for testing and diagnostic purposes. Their usefulness will depend on what you're doing, and in many cases you won't need one at all. But it's still nice to have one built in just in case. But now let's talk about some of the negative aspects of this budget scope. Since this is such a small device, that means you might have difficulty reading from its tiny 2.4-inch display, in which case I suggest getting one of the more expensive scopes I'll be showing here in a minute. Also, its construction is questionable, as it only has a top and bottom plate with an open-ended frame on the sides where small objects can easily get stuck inside. Also, it comes with extremely limited controls and buttons, making it difficult to learn how to use. And according to some of these reviews, it doesn't even come with instructions explaining how to use it either, so it might not be the best choice for beginners. However, I was able to find several YouTube videos covering this scope, so it shouldn't be that much of a problem to learn how to use it. Overall, this scope appears to be a great value for the price. So if you're on a budget and just want something basic to get you started, this looks like a good choice. But now let's look at a more expensive portable scope. This model is the 2C53P, and it has a larger 4.3-inch touchscreen, which makes it easier to use, and it boasts an impressive 50 MHz bandwidth. It also contains 2 channels, so you can measure 2 different signals at once. And this is a standard feature normally found on the full-size benchtop scopes. Like the previous scope, this one also comes with a built-in multimeter and signal generator, which is nice to have. Now, although this one is quite a bit more expensive at over $100, I think it's worth it if you can afford it, simply for the larger touchscreen and higher bandwidth. But another option in this price range is the 101 3D. And this one is arguably the better value since it comes with a larger 7-inch touchscreen and an impressive 100 MHz bandwidth. When it comes to portable handheld scopes that are still affordable, this model appears to be one of the best ones available and is very high quality. So if you've got the cash, then I suggest getting this one if portability is important to you. But if you're serious about getting into electronics projects and want a more professional quality scope that an engineer would use, then I suggest getting a benchtop scope. The Handtech DSO2C10 is a highly rated entry-level benchtop scope that offers 100 MHz bandwidth on dual channels, and it costs less than $200. This is a full-size scope offering extensive controls, making it easier to use than the handheld scopes. Benchtop scopes also offer more features and settings, which will become extremely valuable once you get into more advanced projects. And finally, the last scope on my list today is the Siglent Technologies SDS1202X-E, which boasts an impressive 200 MHz bandwidth. Siglent is a highly respected brand in the world of oscilloscopes, so this is something that you'd find in a professional lab setting inside a company or university. But keep in mind that this is still an entry-level model, and Siglent and other respected brands also sell much more expensive scopes that can easily cost several $1,000s. But for someone working on projects at home, these expensive scopes are extremely overkill. And even this model I'm showing now is probably overkill for a lot of home projects. At $350, it's by far the most expensive scope on this list, but if you can afford it and want an extremely high quality scope, then I highly suggest getting this one. But I should also mention that there are a ton of other good options available in this price range, and you can't go wrong with a lot of these other scopes as well. But the scopes I just showed appear to be some of the better ones based on my research and after reading a bunch of reviews. So now let's move on to the demo part of the video where I'll explain how to use a benchtop scope. I'll be using a Tektronix TDS1012B. Tektronix is another highly regarded brand, and this is another scope where you might find in a lab at a company or a university. However, this model is kinda old now, and it was first released about 20 years ago, but it still holds up pretty well. Back then it probably cost around 1 or 2 grand, but I got mine used on Craigslist about 5 or 6 years ago for only $150. Even though its LCD screen isn't great and might be kinda hard to see, the scope is extremely accurate and it does everything I need it to do, so I'm still pretty happy with it. Now, like I mentioned, the handheld scopes I showed have very limited controls or contain a touchscreen, unlike benchtop scopes which provide a full set of physical controls. If you purchased a handheld scope, then obviously this guide won't go into all the details on how to use your scope, but the concepts are the same, so this guide should still be useful. And likewise, if you purchased another benchtop scope from a different brand, then the controls might not be exactly the same as mine, but they'll still be extremely similar and will be more or less the same for all intents and purposes. Also, keep in mind that this is only an introduction showing the basics of how to use a scope. There are a ton of additional features and functions which I won't be going over in today's video, but the stuff I cover now will be enough for the majority of the projects I have planned in future videos. So for this part of the video, I've switched over to a lapel microphone that's on my shirt, just to make it easier for me to move around, but I noticed that the audio quality is a bit worse, but hopefully it's good enough. So let's get started. The first thing I'll do is turn it on. And since this is an older model, it takes a few seconds to start up, but let's start with the probes. So as you can see, this is a 2-channel scope, and these probes are slightly different, but every probe will have 2 pins, a ground, and you can see this ground is this little alligator clip, and this particular probe has kind of a needle tip sticking out, and this probe is meant to make it easy for you to touch different parts or different traces of a circuit easily. Meanwhile, the other probe here also has an alligator clip for the ground, but it also has a clip on a probe at the tip here. So this is meant for clipping onto a wire or anything that you're trying to measure, and it'll stick there. Like it'll grab onto it, sort of like an alligator clip. But other than that, all probes are pretty much the same. Like I said, there's 2 pins, a ground, and a signal. So for this first example, I have a Raspberry Pi here that's outputting a square wave that's roughly 500 Hertz. So to connect it, I'm actually going to use this probe here, and I'm going to use this alligator clip on the tip here, and clip it onto the signal from the Pi. And then since the ground already has an alligator clip, I can just simply clip it directly onto the ground wire from the Pi. And as you can see on the scope, it is picking up the square wave perfectly. We didn't even need to do anything. But this usually won't be the case. Most of the time you'll need to kind of zoom in or zoom out and adjust it so you can get a good view of the wave. Because, for example, a lot of times you might connect your signal to the probe and you turn it on, and what you might see is something like this. You know, it's just a big block, like you can't make out any information. Now, normally the only thing you need to do like 90% of the time or a lot of cases is simply hit the auto set button. So I'll hit that now, and what this does is it analyzes the signal and determines what the best settings for it are. So this is what it came up with, which is pretty good. We can find out all the information we need from this signal, but we can make a few small adjustments to make it easier. So let's go over that. So you can see here there's vertical position and horizontal position. And each channel has its own vertical position, but they share a horizontal position. So let's first talk about what these squares mean, because that's directly related to the vertical and horizontal positions. So if we look at the x-axis, this is the time domain. The y-axis is the amplitude or the voltage. Now, at the bottom here, we see this m 1 millisecond. So since this is in the unit of time or seconds, this tells you the value of each square on the x-axis. So if we go from the middle point to the end of the first square, this indicates 1 millisecond of time. Since that is what is being displayed here, that's what it's set at currently. And if we look at this channel 1, 2 volts, that's telling us the value of each square in the y-axis. So if we start from the middle and go up 1, that is 2 volts. So when we adjust the vertical position here, we're adjusting the y-axis value. So I'm going to turn this clockwise, and we can see that the height of the signal jumped up. So now down here you see channel 1 equals 1 volt. So now each square in the y-axis represents 1 volt. And the Raspberry Pi outputs 3.3 volts. So this makes sense. 1, 2, 3, a little over 3 volts is what this is telling us. And if I were to switch back to the original position where each square is 2 volts, again, it's still the same reading. You know, if each square is 2 volts, well, this is a little under 2 squares, so it's the same voltage reading, it's just a different scale. And I think that's the most important word to understand what the vertical and horizontal positions do, is that they adjust the scale, but it's still the same reading regardless. So let's switch back to make the signal bigger, because it's easier to read and we get more accurate results if the signal is filling up more of the screen. Now the other thing we can adjust here on the vertical position is where the center is. So normally, I mean, if you're dealing with AC signals, you want the middle or 0 volts to be in the middle of the signal like this. But this is a DC signal. It oscillates from 0 volts up to 3.3 volts. So the way we had it like this is probably better because it indicates that it's a DC signal. But of course, you can adjust this however you want. And actually, for example, if you're dealing with a biased audio signal, so if we were to look back at some of my previous videos, I explained using resistors to bias an AC signal so that it works with DC components. Well, in cases like that, you might want to reduce the vertical position down so that your bias is sitting in the middle. But we're not dealing with that right now, so yeah. Now let's talk about horizontal position. So this is basically works the same way. It adjusts the scale, but this time it's on the x-axis. So if I were to move it clockwise 1 notch, we can see the signal is stretched out and is bigger. And we will also see this M is now reading 500 microseconds. So now each square represents 500 microseconds, as opposed to before where each one represents 1 millisecond. It's just adjusting the scale. So you would want to adjust it to make it so you can see at least a few of these cycles. So this is probably the best setting to have. If you wanted to really like get more detail and do more accurate measurements, you could zoom in like you see here. So yeah, that is kind of the most important controls to know like I said, once you hit the auto set, and again, you want to make sure you are already outputting a signal before you push auto set, because it analyzes the signal to determine the best settings. If it's not picking up a signal and you push auto set, then it's probably going to change it to some weird settings. But let's kind of go over some more details in case, because auto set might not always work. So it's good to understand some of the other settings in case you need to manually adjust it. So, oh, also, before I get there, let's look at this frequency. So you can see here 469 hertz, which is pretty close to 500 hertz. But the reason why it's not exact is because right now I'm creating this square wave using a Python program. And the thing about Python programs is that they, or any high-level programming languages, basically the operating system is in the middle of the Python program and the hardware. So due to things like scheduling, you can't get extremely accurate timings from a Python program. Now, most of the time, this doesn't really matter because when you're dealing with, let's say, tens of milliseconds, or, if you're concerned about a timing that needs to be within, let's say, 10 milliseconds, well, that's slow enough where the operating system and its scheduler won't slow it down. But since I am trying to get a 500 hertz signal here, we're dealing with on the order of 1 or 2 milliseconds. And now we're getting to the point where it's fast enough where the scheduler can slow it down. Now, I'll be talking more about this in a later video, but to get extremely accurate square waves from the Raspberry Pi or other microcontrollers, we will need to use something called hardware PWM. And what that does is it runs entirely independent from the operating system. So basically, we would set, in Python, we can set the hardware PWM or the hardware timers to run at a certain frequency. And once we set it, the timers will run independently without any interruptions from the operating system. And that in that way, they can be much more accurate. So using hardware PWM is very common for controlling things such as servo motors and other things. But the reason why I didn't use that in this example is just to show you, the code is running basically a software timer. It sleeps for 1 millisecond, turns on the pin, then sleeps for 1 millisecond and turns off the pin. So if you remember the formula for calculating frequency, it's 1 over the time of one entire cycle. So one cycle would be from start to finish. 1 millisecond plus 1 millisecond equals 2 milliseconds. That's the period of the signal. And if we plug it into the equation, 1 over the period, we get 500 hertz. And that's basically what we're seeing here. This is 469 hertz, which is extremely close. That's what we would expect. And if we look at the wave itself, we get the same results. Since the x-axis is currently set so that each block represents 500 microseconds, we can see the high part of the wave is roughly over 2 blocks long, and the low part is also about 2 blocks long. So the total length and time of one cycle is about 4 blocks, or about 2 milliseconds. All right, so back to the oscilloscope settings. Let's go over another setting here, which is called single sequence. So let's say, for example, again, like you have a sensor and you're waiting for the signal to go high and you don't know exactly when it will. I'm gonna kind of simulate that with the Raspberry Pi now. So give me a second here I'm gonna stop this program and run a different program. And what this program does is it just outputs a high signal for an extremely short duration, and it's just going to do a single cycle. Okay, so I'm going to run it now, and you'll see on the scope. Okay, so you saw something there just for a split second, but then it went away. Now, in a lot of cases, you would want to pause it there and analyze, like, how long did that signal last, or what was its amplitude. But you don't really have time to pause it. You could run this. You could push this button here, run/stop, and that will pause the signal on whatever was there. So you can see now the noise stopped moving. Everything is stopped. But of course, when you're dealing with a really fast signal, it's really hard to push that button at the exact moment in order to capture it. So we can do something called a single sequence. So I'm going to push run again. It's running. And before we push the single sequence, we need to set the trigger level. So I'm going to adjust this. You can see as I move this trigger level knob, it's adjusting that arrow on the side here. So we're basically telling it, look out for this amplitude. So I'm going to set it, right around, I'd say around half of the voltage that you're expecting is a good place to set this. So this is right around 1.5 volts. Now I'm going to push single sequence. Now let's run the program and see what happens. So as you can see, it paused and we have a really good reading of the signal. Now we can determine its exact amplitude. Of course, it's around 3.3 volts. And we can analyze the time that it was on. This, of course, is the same as the previous square wave, except it's just a single sequence. So it's about 1 millisecond, as we would expect from the code. So those are pretty much the main functions you need to know for a lot of different projects. The other thing I should also show is the second probe right now is turned off. So if I push channel 2, this turns on the second probe. So now you can see we have 2 signals here. And so if we wanted to measure 2 signals at once, then we could go ahead and connect that probe to something else and we can see both signals displayed at the same time. And if you wanted to turn a probe off, just push channel 2 menu again and it disappears. Now another thing I should quickly mention is that many probes have a switch to select the attenuation. In most cases you'll want to leave it on 10x unless you're dealing with a very weak signal, in which case you'll want to switch the setting to 1x. But doing this also decreases the impedance, which isn't desirable because it'll increase the interaction with the circuit. So again, in most cases you'll want to keep this setting on 10x. Some scopes might also require you to change this setting on the scope itself, as you can see here. So now, just for fun, let's see what the audio output of my PC looks like while playing a song. So here I have a standard 3.5mm stereo cable, and here I have a jack with the breakout of the wires. So we have a left channel, right channel, and the middle one is ground. So I'll simply connect the tip of the probe with an alligator clip to one of the channels, and then I'll connect the ground to the ground cable. Alright, so now I'll play a few seconds of a song that popped up in my feed from a band called King Gizzard and the Lizard Wizard. If you haven't heard of them and are into rock, then you should definitely check them out. Let's see how it looks on the scope. So I think this signal looks pretty cool, but to be honest, it's difficult to gather any useful information from this except for the amplitude. This is because there's a ton of different frequencies contained in the signal and it's become too complicated to analyze. This is where more advanced functions come in. And to be specific, this is an example where you might want to use the FFT function, which stands for Fast Fourier Transform. This graphical representation is completely different than before. Instead of time being the x-axis, we now have frequency in the x-axis, while the y-axis still represents amplitude. So if we look at this image as an example, we can see this signal is dominated by frequencies of about 1 kHz. But there are also spikes in a bunch of other frequencies, since this is a complex signal with a lot going on. Now, the reason why I won't be going into more detail on FFTs right now is because not every scope will have this feature, and the scopes that do will likely have very different menus to configure it. Also, its usefulness will depend on the specific application you're working on. For audio, it's certainly useful, but for the sorts of projects I have planned right now, they mainly focus on robotics and home automation sorts of projects where the time domain is typically more useful. Also, this video is getting really long now, so I think it's a good time to end it. But the other thing I wanted to quickly mention is that many scopes also have various connectivity protocols including USB and more. This means that you can control the scope and record data directly from your PC. But again, the steps to do these things will probably be very different depending on the scope. But anyway, that wraps up today's video. The demo part of this video might have been slightly disjointed, but hopefully it made sense. If you enjoyed the video, then be sure to give it a thumbs up and subscribe to the channel if you haven't already. Also, if you have any thoughts or questions about the topics covered, then feel free to drop a comment. As always, thanks for watching, and I'll see you in the next one.